we're going to show how to determine the convergence of this series using the integral test. Assuming this is positive and decreasing, then the obvious function that we'll use is arctangent of x over x squared plus 1. So we are really interested in doing this improper integral from 1 to infinity f of x dx. And this is done the proper way by first taking the limit as b goes to infinity of 1 to b of f of x. Now I'm going to write what f of x is. So I'm going to work on the side, the antiderivative of that thing, and then come back and fill this in like this. If I know what that is, 1 to b. So this is the antiderivative that I'm interested in that I said to work on the side. Looking at this, I think the most appropriate way to do this would be to try u substitution. If I let u to be the numerator, du will turn out to be that. So this is really an integral u du, right? Because du looks like that. This is a u, there's a du. And we know how to integrate that. So basically, the antiderivative of that is half the arctangent of x quantity squared. So remember what this is. Let's try to put it back into our improper integral. All right, we're back. Remember what that was? Half of arctangent squared. So basically, that is the limit of half of arctan of b squared minus half of arctan of 1. We know what arctan of 1 is. Pi over 4. Okay, what happens when b goes to infinity? We know this. When b goes to infinity, the inside becomes pi over 2. We don't have to be too concerned about simplifying this because we're only interested whether this improper integral is converging or diverging. It's not an infinity. This is a nice number. So we know that the improper integral converges. And because of that, by the integral test, our original integral, our original series, which looks like that, also converges. Sorry about that. This is how we prove the convergence of this series.